Now, the basic building block of this cascaded H bridge multilevel converter, in short CHB multilevel converter or CHB converter, is H bridge, which we have shown in this diagram here, and we have also studied it earlier how H bridge works. I have shown generic switches here S1, S2, S3, S4. Basically, each of these switch is a combination of a transistor and an anti-parallel diode. Okay. So, I mean this switch is it can be, say, if I do with a IGBT, each switch is like this. Okay. We have seen that. This H bridge is the basic building block of the CHB multilevel converter. It also has a DC source which is represented by VDC. In some cases, this DC source can be capacitor, and in some cases the DC source can be fed from a rectifier. In some cases it can also be, for example, can be connected to a PV energy source or PV panel. This building block or this H bridge is sometimes called a cell or a module. Okay. And the CHB has many cells connected in series. The word itself says cascaded H bridge. So, we are cascading several of these H bridges together. We are series connecting them, cascading, series connecting. The DC link of each cell is isolated. So, when we cascade them, I will show you, when we cascade them, we have isolated DC links for each of these cells or modules. Now, each cell, if you see, each cell produces 3 levels of voltages. So, this is the output of the cell. Okay. Here is the output of the cell, and if so, here this voltage can assume 3 levels. I mean 3 distinct magnitudes of voltages are possible at this point here. So, suppose if we turn on S1 and S3, okay, if we turn on S1 and S3, then this voltage here is 0, right, because this is connected to this and then this is connected to this. Similarly, if we can turn on S2 and S4, the voltage here will be 0. If we turn on S1 and S4, if we turn on S1 and S4, that is the diagonal switches, or S2 and S3, we can get either plus VDC or minus VDC. So, by turning on these diagonal switches, we can get plus VDC or minus VDC. So, for example, if S1 is turned on and S4 is turned on, and this voltage, if I say VAB, so if we turn on S1 and S4, then VAB voltage will be equal to plus VDC. In this case, VAB voltage is plus VDC, this one. Okay. On the other hand, if we turn on the S3 and S4, if we turn on S3 and S4, then the VAB voltage is minus VDC, this one. Okay. And of course, when we connect, when we turn on S1 and S3 or S2 and S4, we get 0 voltage here. So, there are 3 voltages available from one H bridge or one cell. Of course, we cannot turn on S1 and S2 simultaneously or S3 and S4 simultaneously, then we will short the DC bus. So, S1 is complementary to S2 and S3 is complementary to S4. This we have to maintain all the time. Now, what will happen if we connect 2 such H bridges together? Okay. So, we have now H 1 and we have now H 2, and we have connected two such H bridges together. How did we connect? This was the output of one H bridge, and this one is now connected to this point, and this is the output of the second H bridge, and we have connected them in series. So, VH1 and VH2, the voltage possible from VH1 and VH2 are independent of each other. So, VH1 can have 0 VDC or minus VDC, that we had seen earlier. What about VH2? VH2 is operating independent to VH1, so it can also generate 0 VDC and minus VDC. Now, what is the voltage VAN? What is the voltage VAN? VAN is nothing but the sum of VH1 and VH2. So, we can make this sum. So, I take 0 here, suppose VH1 is 0. So, 0 plus 0 is 0. So, this is one possibility, 0 and VDC is VDC, this is the second possibility, 0 and minus VDC is another possibility. Okay. Take now VH1 as VDC. So, VDC and 0, VDC plus 0 is VDC, we have already written this, VDC plus VDC is 2 VDC, and VDC plus minus VDC is 0, which we have already written. What is the third option? VH1 is minus VDC. So, minus VDC plus 0 is minus VDC, this is written here, minus VDC plus VDC is 0, written here, and minus VDC and minus VDC is minus 2 VDC. So, we see that VAN can have 5 levels of voltage, 0 VDC, minus VDC, plus 2 VDC and minus 2 VDC. So, with 2 cells, number of levels in VAN is 5. So, there is a mistake here. So, this should be 5. With 2 cells, number of levels in VAN is 5, and these are the 5 possible voltage levels. Okay. Now, if you connect more number of cells, say if you generalize it, if you connect n such cells, then number of levels in VAN will be 2n plus 1. Now, remember that the voltage rating of each switch in each cell is VDC. Why the voltage rating is VDC? Because if you, for example, turn on this device, the voltage that needs to be blocked by S2 is VDC, and hence the voltage rating of each switch, I mean these switches are all identical, the voltage rating of all of them is VDC throughout, and the current rating of each switch is equal to I load. I mean, if we connect a load here, for example, suppose we connect a load here across VAN, then this load current will flow, either means it can flow through any of these 4 switches, and it can also flow through any of these 4 switches based on the switching combination. So, the rating of these switches will be equal to I load, where I load is this one. So, we see that all the switches are identical in terms of their voltage and current rating. The voltage rating is VDC and the current rating is I load. So, this is one feature of such converter, in that is that this converter has a high degree of repetitiveness, or in one way we can say it is highly modular, because H 1 and H 2 these are two identically rated H bridge cells. So, if we produce one such H 1, we can very easily manufacture H 2 or H 3 or H 4 like that. So, it is highly repetitive and modular in structure. So, it is very advantageous to produce such cells in mass production, and it is whenever you can produce any product in a mass production fashion, then the cost reduces substantially, because you need to produce one such cell in a very detailed and with a considerable time and effort. But once that cell has been properly manufactured and tested, then it is a matter of repeating the process and producing many such cells. So, we see that the CHB has inherently this feature. So, how do you now connect, or how do you get a 3-phase converter? I have shown this with 3 cell CHB here. So, this is for example phase A, this is phase A, this is phase B, and this is phase C. This is the load here, here is the load, and here is the converter here. Okay. So, in phase A we have 3 cells, cell 1, cell 2, cell 3 here. These 3 cells are cascaded. So, you can see that the output of cell 1 goes to the input of cell 2, output of cell 2 goes to the input of cell 3, and so on. So, there are 3 such cells in each phase, and altogether in 3 phases we have 9 cells. Note that all these cells have isolated DC sources. So, all of them are fed from isolated DC sources. We will see how these isolated DC sources are made. You can have more than 3 cells, you can have 4 cells, 5 cells, 6 cells like that, and you can then have a generalized n cell cascaded H bridge. One point to note is this neutral point here. Okay. The end point of this A phase, B phase and C phase are connected together at this end point here, neutral point. This neutral point here is isolated from the neutral point of the load. Usually they are all isolated, and there may exist a potential difference between this point here and this point here, the load neutral point and the converter neutral point. We can also, we will see sometimes later, that because this capital N and small n are isolated from each other, we will during fault operation it is possible to bypass some of the cells, and we can have a common mode voltage which takes the benefit of isolation between capital N and small n. We will see that later. How do we, the real converter looks like? Say for example, we are supplying to a motor load here, and this is says B phase, this is C phase, and this is A phase, which is shown with the detailed circuit. And if you see one cell in phase A, these are the 4 transistors or IGBTs with anti-parallel diodes, but the DC link here earlier we had shown with a battery symbol, but often this DC link is made with rectifiers. So, 3 phase rectifiers with a capacitor here, that forms the DC link. And this DC link is isolated from the DC link of the next cell and from the next cell. We often have a transformer which has a primary and several secondaries like this, and these several secondaries or each secondary is connected to the respective rectifier. So, we have similar arrangement for cell in B phase and for cells in C phase. So, basically it is quite a big converter with input rectifiers, capacitors, and then cells, and then these cells are connected in cascade. But this transformer with one primary and several secondaries actually helps in improving the power factor of the current which is drawn at the transformer primary. So, basically it is a multi-pulse rectifier, and the THD or total harmonic distortion of the current drawn from the input is very small. We will talk about it sometime later, not while discussing about CHB, because in CHB we will be focusing more on this side here, where we will assume that there is a stiff DC source with a battery, and then these cells are connected in series. So, here we are showing detailed circuit for getting the 5 levels of CHB. Suppose we have a 2 cell CHB, and so the VAN voltage here is, as I had earlier told you, is equal to VH1 plus VH2, and so if we so this is also shown in this table here, the same thing with the detailed switches, the status of all the switches also shown. So, if VAN is 2 VDC, of course, VH1 will be VDC and VH2 will be VDC, and so in order to get VH1 as VDC, we should turn on S1 and S4 as shown here. And similarly, if we want to get minus 2 VDC in VAN, then we need to have VH1 as minus VDC and VH2 as minus VDC, because their sum will be equal to minus 2 VDC. In order to get minus VDC, we should have S3 and S2 turned on as it is shown in this diagram, and from this second cell S3 and S2 turned on. This diagonal switches in these 2 cells will give us this minus VDC. So, minus VDC and minus VDC and like this. In a similar way, as we have written here, so this was for VAN equal to 2 VDC or minus 2 VDC. That means, this circuit are showing the status for this one and for this one. Now, if we want to get this VAN equal to VDC, how is the circuit? It is shown here. Now, for VAN equal to VDC, that means I want to get VDC voltage here, then there are several possibilities. In fact, there are 4 possibilities. What are these 4 possibilities? The possibilities are VH1 is VDC and VH2 is 0. This is one possibility. The second possibility is VH1 is 0 and VH2 is VDC. Okay. So, this is what is shown here. So, VDC, when we want to get VAN as VDC, it can be VH1 VDC, VH2 0 or VH1 0 and VH2 VDC, because VAN is nothing but VH1 plus VH2. Now, for getting VH1 as VDC, and we have one switching combination, that is S1 in H1 is 1 and 0, H3 is 1. So, this is the these are the two switches. If we want to get VDC out of VH1, then we have to turn on this S1 and S4. But when we want to get 0 from VH2, then we have two switching state possibilities or two switching combination are possible. Either we turn on S2 and S4 or we turn on S1 and S3. Both of them will give me 0 out of VH2. So, there are two switching state or switching combinations possible in order to get 0 voltage, or we can say that in order to get this combination VDC and 0, there are two switching multiplicities possible. The word multiplicity is used here, okay, that there are two switching multiplicities possible in order to get this VDC and 0. Similarly, if I want to get we can also get VDC by making VH1 as 0 and VH2 is VDC. Of course, VH2 equal to VDC, there is only one switching multiplicity possible, which is the diagonal element, which is shown here, this and this S1 and S4 and S1 and S4, these are turned on. But for getting the 0 from VH1, we have two multiplicities, and these are either you turn on S2 and S4 or you turn on S1 and S3. This is shown here. These are the two multiplicities. Again, in a very similar way, if we want to get VAN equal to minus VDC, then we can have VH1 as minus VDC, VH2 0, or we can have VH1 0, VH2 minus VDC, right. This is shown here, VH1 minus VDC, VH2 0 or VH1 0 and VH2 minus VDC. Sum of both is equal to minus VDC. And then we have similarly 4 switching multiplicities which can produce this VAN equal to minus VDC. If we want to get VAN equal to 0, then we have even more multiplicities. See, if we want to get VAN equal to 0, we can have VAN equal to VH1 0, VH2 0, we can have VH1 VDC, VH2 as minus VDC, because the sum of these two will be equal to 0, and we can also have VH1 minus VDC and VH2 as plus VDC, again the sum of these two is equal to 0. So, now if we see this combination, if we see that VH1 we want to get VDC, we have only one multiplicity, that is this 1001, which I think is this figure here. Okay. We have connected the diagonal, this diagonal and this diagonal, and you see that the voltage produced by H1 is opposing the voltage produced by H2. Okay. One of the H1 is producing plus VDC, while H 2 is producing minus VDC, and they are opposing each other, so that the net voltage VAN is equal to 0. Similarly, this sixth combination which is shown here, H 1 produces minus VDC and H 2 produces plus VDC, and they are their total is equal to 0. Now, for the 0-0 combination, when both VH1 and VH2 are producing 0 and the sum is also 0, and then for the 0 combination we have two multiplicities, and those multiplicities are elaborated in the table and also in the circuit. So, summarizing these multiplicities, we can see that this is the table which is summarizing with all these multiplicities. When we have 2 VDC, when we have VAN equal to 2 VDC, we have only one possible switching state, that is, therefore, there is only one possibility and this is one multiplicity. When we want to produce VAN as VDC, then we have 4 multiplicities possible, that is 4 switching combinations possible. When we have VAN equal to 0, there are 6 multiplicities. When we have VAN equal to minus VDC, then we have 4 multiplicities, and when we have VAN equal to minus 2 VDCs, we have only one possibility. Now, so we see that when we are going with a higher voltage, we have less multiplicity. When we are going towards 0 voltage, then we have more multiplicities. Why are these multiplicities useful? These multiplicities are useful in a variety of situations. For example, you may think like that, suppose here we have shown these DC buses as stiff DC sources. Suppose they are made up of capacitors. Okay. For example, we are connecting this Cascaded H Bridge converter in a STATCOM application, where we are only injecting reactive power, for example, in a transmission line. Then we have capacitors, and these capacitors will continuously charge or discharge. Now, these multiplicities can be used there to charge or discharge the capacitors, okay, or it can bypass. For example, suppose we take this example, VAN is equal to VDC, we would like to get VAN equal to VDC. Now, you see that in one case VH1 is VDC and in other case VH1 is 0. Now, if you have VH1 as VDC, if you have VH1 is equal to VDC, this means that this diagonal switches are on, which means that suppose this is a capacitor, this is made up of capacitor, the capacitor is present in the circuit, the current will flow, the load current will, because the diagonal switches are on. So, the load current will, for example, if it is coming like this, it will come here, go like this, go through the capacitor and come out like this, if the load current is going in. On the other hand, if the load current is going out, then it will come through here, go through this switch, go through the capacitor and go out like this. So, depending on the direction of the load current, whether it is going in or going out, the capacitor charge can be changed, or the voltage on the capacitor can be changed. But on the other hand, if I use this multiplicity instead of this plus VDC multiplicity, if I use this one, then I can completely bypass the capacitor, because when we are getting 0 voltage, essentially we are turning on either the lower 2 switches or upper 2 switches. So, which means that the current will come here, will go through this switch and will come out like this without changing the voltage of the capacitor. it will not go through the capacitor. So, if we see, for example, if the capacitor voltage is going up and I see that I have two multiplicities in my hand to produce the same voltage VDC from the converter, then I know that the direction of the current is such that it will further increase the voltage on the capacitor, because at that point of time, suppose the direction of current flowing into the cell is such that it will further increase the voltage on the capacitor, it will inject more charge into the capacitor, then in that case I will use this multiplicity instead of this multiplicity. I will choose this one, because in that case I am able to bypass the capacitor, so that the voltage on the capacitor is not further increased. The reverse is also true. Suppose I am in a situation where I am seeing that the capacitor voltage is going down and I want to immediately charge the capacitor, and I see that at that point of time the direction of current is such that if I choose this multiplicity, then I will be able to charge up the capacitor quite quickly. I will choose that one instead of the second one. So, therefore, this multiplicity can be used to balance the capacitor voltages, for example, if it is a STATCOM application. For other applications, you can also redistribute the losses in the cells. Okay. So, you can control the rise of temperature and the losses, you can redistribute the losses. For example, if you are in the 0 state, you have several switching multiplicities possible, and by effectively using them, you can make sure that all the cells in this H bridge or cascaded H bridge have equal temperature rise. Okay. This is an important criteria, because these cells are all modular in nature. You can understand from the circuit diagram itself that the cells are modular in nature, and when we say it is modular in nature, it means that they have identical construction, including the construction of heat sink. So, they have identical gate driver board, identical, for example, rectifier or capacitors, and identical heat sink and identical enclosure and everything. They are all modular and identical. So, when we put many of these cells and when they are working together, you do not want one cell to be heated up very high as compared to the other cells which are much cooler. Okay. Then because then that cell will be stressed more, its temperature will rise more, and again the longevity will go down. So, it is important that with such converters, the loss distribution is also uniform for each cell, it is equal in all the cells. So, this can be achieved by rotating this pattern through the multiplicity. Okay. So, there also multiplicity plays a role.